Hello, this is John, and this is my 7th video assignment of Fundamental Semiconductor Device 2. And today we're going to talk about the punch-through, which is one of the short channel effects in MOSFET. So, we're going to talk about punch-through with those figures, which is the MOSFET that has a long channel, long gate length, and the short gate length like this. So when the MOSFET looks like this, there will be a depletion region for source and drain in long channel. But if the gate length gets shorter like this in here, then the depletion region will make made like this, and here like this. There will be an overlap of the depletion region. So this is the problem. When there's an overlap in these depletion region, then the channel that has to be made in the interface, which is the surface of MOSFET, will made in the body part. So there's a path, then the carrier or current get flows or made in the body. So it will be a leakage current, and this is a punch through that we're gonna talk about today. So this is a very big problem of the MOSFET because if there is a leakage path in the body, then the sub-threshold swing will be bad when the punch through happens, right? When the punch through occurs, So we have several solutions to solve these punch through problems. And for the first, we can just think about the depletion width and the doping concentration relationship. So as we learn in Fundamental Semiconductor Device 1, when the doping concentration gets higher, the depletion width gets shorter. And when the doping concentration is low, then the depletion width gets longer, right? That's wider, I guess. And so, with these common facts, we can think that we can increase the body's doping concentration and make the depletion width in the body lower, with the body smaller. So, so the overlap will not occur in the body part. So this is kind of clever solution, but there's some problems. So we don't use this as much. So here's the deal. For the first, when when we heavily dope the body, then the body will have a fixed charge way will have many fixed charge than before. Then these fixed charge will make a Coulomb force that interrupt the currents move source to drain. The carrier moves source to drain. It interrupt them, so it means the resistance of the body gets higher, and it occurs the RC delays higher than before, and that means this device will how do I say it? Will get slower than before because the frequency will be smaller than before. So here's the first problem of the solution. And the second one is when we heavily doped the body, then In the N-flat, the source and drain will be heavily doped with the N-type, and the body will be heavily doped with the P-type. So there will be a PN junction, which is made with a heavily doped N plus, and P plus. And when the N plus and P plus made a PN junction, then it will make uh, it will make bigger. It will make very big, very high electric field than before. And when the high electric field will occur, then when we draw energy band, when the electric field is higher, then the slope of the band will be bigger than before, so the thickness of the band will be thinner. So for the carrier, for example, for the electron can tunneling and get through the thin energy band, thin energy barrier, so we can make a tunneling like a BT-BT. So it will occur leakage current. So that's the main problem of the solution that increase substrate doping. So we have another solution that called as a silicon on insulator. So which is this. So there's a substrate and there's a gate, and we're gonna put the oxide layer in the substrate like this. So we can just cut the leakage current path in the body. So when the oxide barrier looks like this, the carrier in here cannot jump through the body, so it can it can act as a barrier for the carrier. Barrier as a carrier. That's kind of rhyme, but we don't use this solution either we don't use this solution either because the substrate price is way higher. Substrate is too expensive for the silicon on the insulator. And also, when we apply this silicon on the insulator solution, the device layer will be thinner. So when the device layer will be thinner, the series resistance will get bigger. So it means the current will get lower. Third problem, there's a self-heating problem that the Joule heating will occur in the device. And so these are the reason that we're not using silicon insulator, the SOI solution that much. And for the last, we have a strain relaxed buffer solution. So, which is the concept is this. So, we're going to use two materials in substrate that has different energy gaps. So, when we attach two materials that has different energy bands in substrate like this, then we can draw energy band like this. So which is the so here will be different energy band gap. So as we made this structure, then these energy band gaps, I mean the difference of energy band gaps between two materials will work as a quantum well. So the carriers captured will stuck in this place. So it cannot move to other part like bodies or something else. so it can cut the path of the punch through. But but this solution is also require the high prices because we have to make the substrate with two different materials, and we have to attach this and make the one substrate. So the tech, so it's kind of hard to make a substrate. So make one substrate with two materials. So the price gets high. Price will be higher to make the substrate than when we use the single Si substrate.